All right, I want to give you guys an overview on the procedure that I've been using in order to get more clarity on what the concepts of nature mean and try to put this story together, right? For many reasons, but also so you can help improve it if you can find a way to improve. But also, what I want to point out is this procedure does something for us in our scientific search. So I guess I should back up what our scientific search is trying to cover, right? So humans have explored our reality through our lens, right? Our slowly changing lenses. But what's changed the lens? What's made it so that people for generation to generation would hold certain kind of story and relationship with reality, right? Think a certain way and then transition. Well, most of it's been our psychotechnologies that people have discovered, right? So a new conceptual, systematic way of framing things and therefore extracting information, better at looking for patterns. If you have a better systematic way of framing, there's more pattern recognition possible in it, and so on. So every new psychotechnology, every new way we've come up with of adapting the brain we currently have to think in a different way, to put things together slightly differently, and found then as a consequence that it maps better to the real world. It gives us more predictability. It's more accurate to what we think we're seeing or measuring, right? Because that's a big problem too. When we're seeing in the world, the start place is we're seeing, which means we're imagining and making it up. And it's not that we're making it up from this will to just to want something. We're making it up from the best way we've learned to put it together. From when we were a kid and we started, oh, does it do that every time? Right? And we started to figure out what the real patterns were versus the patterns that look like patterns, but then when you look closer, they go away.
Yeah.
Okay? So the waking up to the idea that there are real patterns versus things that I see all the time that when you look closer, they go away. Right? It was kind of the awakening of science. And the first scientist in our history, in humanity's history, was, many people would say, Alexander, right? And because he was the first person to imagine a reason for measuring distances or measuring lengths in time. First person, and not just imagine, but then to do it.
Yeah.
So he came up with just the idea of taking a stick, thinking of it as the base, right? And wondering how many sticks from here to there. But think what this does. Up until that point in time, everyone who'd looked into the world had made up their best guess of what it was from their level of interaction with the world and the clarity they've gained from the things they've done so far, right? But they're making up their best guess, and then that was it. That's what the world was to them. There was no further investigation. There was no looking closer, checking against your story, right? He was the first one to say, hey, I see the world like this. That looks like it's about a kilometer away to me. Well, I'm going to measure it. So I'm going to count how many of these sticks it actually is away. And then I'm going to come back over here and say, oh, that's 1.2 kilometers away. I'm going to see it at 1.2 kilometers away now because I've measured it, I filled in way more details, I made a more accurate observation of reality. Now, so he's inventing measurement, right? He's inventing the idea that instead of looking into the world and making it all up the best you can, it's, I can probably find a way to see it better. Right? I can take something and systematically go about taking a measurement and therefore using the measurement, a number, to report something about the world that I didn't know before. And that thing that I report, turns out you can go check and get the same number. So the number has some realness to it. And what it's expressing, no matter who looks, it's there. Versus the story I was telling about reality before I started measuring things, right? No matter who looked, it's always different, unless it's a very general thing we've all decided to agree on ahead of time, right? Okay, so that's the birth of science. This birth of the idea that we should look into the world and try to make sense of it, but also look via measurement. And that we trust measurements more than the stuff we were making up. Why? Because everybody who looks can get that same number, right? If they take it seriously and try, they're going to get the same report about what the world is. Now, what does the report mean? That's the mystery, right? This new thing you saw has to be interpreted. Just like when you're growing up as a child, every new thing in front of you, you need to make sense of, you need to engage with it. So we're going to engage with the mysteries of reality in a way, the mysteries of measurement in a way that I don't know there's it being done otherwise. Okay? Now, to get there, let's remember we have now a modern story of what reality is. We skipped all the way from Alexander all the way to, say, Dirac. Okay? He's brought us to our modern version. And Einstein, and there's lots of people, lots of steps and contributors But our modern picture is pretty much now encapsulated by Dirac's picture, right, of what the electron is, what the base symmetries of quantum mechanics are. And that symmetry equation has, well, it works with very specific Planck constant boundaries, which give us all these constants in nature. Now, those Planck constant boundaries weren't derived from Dirac's equation. This is the interesting thing, right? The constants of nature were where we found the Planck constants. When we take the constants of nature and we look at the dimensions of what they are. So they report a number. So there's always some string of digits, right? That's some number, 1.234. And then there's going to be some sort of scaling factor applied to the number. So the specific string of digits can always be unique, or it can be the same thing over and over. You can repeat it over and over, but then put a different scaling, right, to represent. So numbers, or these measurements we're making of reality, are reported in a number with a scale. And the way we do it in scientific notation, times 10 to the, say, 14 for this number, okay? But this isn't complete. This is a number, so a very specific, precise measurement, and the scale of the measurement, and some sort of units. I could say meters, right? It could be meters per second, or, yeah, let's do meter per second. Whatever the dimensions of the number we're reporting is, with the 3 bits of information. We have a scale, or a number, a string of digits with a scaling, and then the dimensions. But the dimensions are the first thing to really look at, because it's the kind of thing we're reporting, right? If I give you a number, hey, it was 1.2. 1.2 what? This is the what's. This is exactly the thing we're talking about, the relationship we care about. And in this case, it's 2 different dimensions, the dimensions of mass, or meters, the dimensions of meters divided by dimensions of seconds, right? So length divided by time. Okay, now I just made these numbers up, I made an expression, but this is how in science we're gonna systematize the way we report what we find, okay? By using a number and a scale and a dimension. All right, well, we have now a large list of measured constants of nature. What does that mean? That means when we decided, hey, we're kind of done with this whole making stuff up in our head because none of us are getting a good story. It's not, we're not getting further yet, so we need to ask nature, give us another clue. Well, what clues do we have from nature about the story that's still yet to come, the theory of everything we're after? Well, the constants of nature we've measured are our clues, literally. And I mean that as far as I can, literally. If someone were to propose a story that was supposed to count as a theory of everything, that was supposed to give you more insight to the structure of reality and how things are connected and work, and therefore be able to manipulate it more precisely, right? To know it's intellectually better and therefore navigate your old world better. In order to do all this, we have to do what?
Understand what it is that they're saying at all.
Mm-hmm. Yeah, we get a measurement right now. You get 299.792.458 times 10 to the 8 meters per second. That's the actual measurement we would get. So I just made up a number here to represent how we do numbers. But one of the measurements we have, we call a constant of nature, is the speed of light. And let's try to be as explicit as we can about what we know about this thing, okay? This is the measurement, right? The whole thing is the measurement. It's in the dimensions of meters per second. So we have 2 different dimensions we care about. And in fact, this number and scale is reporting a relationship built into nature between these 2 dimensions of meters and seconds, okay? That's literally why it's a constant in nature, because for some reason, it's considered a mystery at this point in history, right? For some reason, this thing exists written in to the relationship in nature between meters and seconds. Cool. We have how many of these things? How many constants in nature do we need to measure and then use that scaling parameter, that number and scale, to put into Dirac's understanding of the electron and quantum mechanics, and then have our modern world? What our current explanation right now is just the Dirac model with how many parameters like this in it?
It's 44, right?
Yeah, there's 44 constants in nature in our whole story in physics, right? So 44 constants in nature, 44 numbers, measurements about what reality's structure and built-in relationships are that need to be translated. Meaning this number right now as it stands probably means nothing to you. Right? Nothing. It's hard to parse. Now you could stare for a long time and say, oh, okay, I'm going to build an association with things that are this big, and to me it means roughly this size. Okay, that means something to you, but why these digits? Why that scale? It's a relationship between these things. What are these things? What are these dimensions, right? Now, let's back up for a minute. How many dimensions are possible? What kind of, out of all the 44, if we listed them all, how many different dimensions would be involved in all of these constants of nature?
A lot.
We would have time, we would have space, or length, okay? We'd have charge, we'd have mass, and we'd have temperature. And we'd have combinations of those. But that's it. That's it. We get everything from just those 5. It's a really big deal. The first thing is when you take all these mysterious clues that we've gotten, the best clues we've gotten about what reality really is, measurement, versus what we're making it up to be, okay? Our best clues only have 5 dimensions in them. What does that mean? That means our current story of reality is a story of how these 5 dimensions fit together. We don't know why, right? We have constants that say that it fits together this way, but we don't have a story for why it fits together that way. We don't have a picture to put with the claim.
It implies a structure.
Yeah, it implies a structure. Of course, everyone's going to assume there's a structure because it's reality. It's persistently there. It's got to have some logic or structure to it, right? But here we're at now. Our base description of reality is coming to our 5 kinds of things we can measure. That's what we mean by dimension. Okay, we mean that there's a measurement type, a thing you can literally go into the world and try to get an accurate number associated with it. Okay, so we found there's 5 things we can do that for. Alexander figured out these 2 were measurable things. Right? Now, before him, literally no human had ever imagined that. What a transition. The birth of science. Where did this come from? He invents what now? If you know that, if you realize that, you're the first one to look into the world more accurately, to take advantage of the fact that you can now measure some things, right? What can you do? Well, he invented the early sundial, therefore the early clock. Kind of a big deal. He also invented maps. Hero of humanity in many ways, right? Maps, not just in the modern form that we put in for Google Maps to get instructions to go somewhere, but conceptually, right? The idea of a map, of looking out on something and saying, I'm going to represent that like this. See what I mean? Yeah, that's
a memory.
Yeah, he's trying to record something, but also a thing that's recordable with measurements alone.
Right, you have to have some metric.
Yeah. Okay, so he's inventing metricizing things. He's inventing science, right?
And computation in the same.
There's a lot going on. Yeah. Just a miracle spark became, what did he say, a wildfire? Of
Oh,
yeah. Yeah. Okay, so the process we're going to do now is we're going to look at the 44 different constants of nature. We're going to list their information. I should say this content here. This one where its digits end, and I didn't do ... because in our current model, we've decided to say, hey, we're going to make everything in reference to the ones we use the most, like the speed of light and so on. So our measurement for that is now going to come the reference, and we say it's 0.00000 forever because of that. Now, what that really means is that we have a precision of reality that goes up to this many significant digits and no precision after that. Okay, so we have measurement error bars in the ones that we didn't make the references. Okay, so all the constants of nature, I could list them, how many digits they have, or their specific digits, but also, well, let's get one, just to make this much more concrete with examples. In fact, I'll pick a particular one that has a lot of significant digits. Let's do... Okay. Let's do RK. 2.58. 128074434 with an error of 84. That's a huge one. Times 10 to the 4. And our dimensions. What kind of relationship are we talking about with that constant? Okay, meter squared kilogram over seconds coulombs squared. Okay, now here's where we're at. Almost everyone, I would assume, sees this entirely abstractly and vaguely.
Yeah.
And that's what we're going to try to get past. We want to find some sort of geometric, algebraic geometric expression that gets us there. That's what we want. And if there's more than one, we're going to keep track of all the ones that could possibly be it, right? We're starting from ignorance. We don't know what it means.
Right.
Now, normally, I would say, most people would say, confronted with the mystery of this, okay, solve it, figure out what it might mean. They would try to go internally and try to come up with some sort of possible thing that might lead to that, come up with some rational story that could get them some leverage to get there, and then find a way to code that story in mathematics, and then therefore use it to make an exact prediction, and then go test that prediction against the actual thing you wanted to explain and see how close you got. And you know, when you try that, come up with 1,000 good stories and finally figure out how to make them perfectly matched in math, and they get a prediction. So you got 1,000 predictions. Your chances of even getting the first significant digit right are very low, right? That method for this, given the sheer ignorance that we're all facing with this kind of thing, this is a constant of nature, a thing we've measured accurately. We know what sort of relationship it's talking about, but nobody knows what that thing is. Nobody knows what that thing is, or that one, or that one. These dimensions themselves, nobody knows what is. But this tells us a relationship between them. But since we don't know what they are, we're kind of stuck, right? What we're going to do is we're going to admit radically to our ignorance and not try to generate a story that could possibly work and then check and hope. And then if it doesn't, oh, we spent our whole life, so we're going to try to go with it anyway. No, we're going to admit that we're never going to make progress that way. We're just going to ask nature directly and try our best to trust it and be good scientists along the way. Now, how do we do this? Well, we use a new superpower that we have, a new psychotechnology that's been in existence for about a decade now, right, or more. My favorite version, or my most familiar version of it, would be Wolfram Alpha. But this is a tool that allows you to ask a mathematical question, which we should back up. When this tool exists, it really behooves us all to learn how to ask mathematical questions, right? How to ask good ones. This is a really powerful art, because before you were stuck in a situation where we had a good question. What does this number mean? Right? But if you don't have a tool like Wolfram Alpha, you could literally be stuck with the you just need to be a genius that somehow comes up with a story that's good enough to make sense of it, versus you can ask Wolfram Alpha questions, right? Now, how could we turn this into a question that we can ask Wolfram Alpha?
Look at the relationship of the units and pretend that one of these is our known, some of these are our unknowns, and then solve for what's known and not known.
Good, good. We start looking for the patterns and trying to reduce information.
Yeah,
now,
normalize something to one.
Okay, we could normalize something to reduce patterns. We can do all sorts of things. Now, the key is, though, if we only had this, though, there's not much pattern to be doing things in. If we have all 44 constants, we have a lot more pattern to start looking for things in.
Where do we have overlap?
Yeah, and the first big step is to notice that they're all only composed of 5 dimensions, and very uniquely, this is the big thrill. When you realize it's all of these constants of nature are best clues for what reality actually is, come from just these 5 different dimensional boundaries, these 5 limits of action. So we have a minimum boundary for time, a minimum boundary for space, a maximum boundary for charge, mass, and temperature. Somehow in there. This is concluded from the measurements of the constants in nature, not assumed beforehand. It's a complete mind blower. No one expected that, right? So we have these mysterious constants or limits of each measure that pop out, and we're going to call them Planck time, Planck length, Planck charge, the Planck mass, and the Planck temperature. So all 5 of them are just going to symbol like this with a sub P for Planck, okay? But they're just the dimensional limits, the bounds of each of these 5 of the dimensions. So here, we're going to look at the prescription of what kind of thing is this constant of nature. what are its dimensions? And from that, we're going to plug in the boundaries of the limits. Okay, we're literally going to go, whenever there's a meters, we know it's what kind?
Blank length.
Blank length, because meters is length. So we're going to put, this one would be converted, we convert that box into Planck length squared, kilograms.
Planck mass.
Planck mass.
Planck time.
Planck time. Planck charge squared. Okay, so this dimensions of our constant. We're going to start with, well, our first guess is going to be, well, it's just literally the intersection of the bounds of reality.
Is charge squared is equal to speed of light squared?
Charge squared equal to speed of light squared? No.
Oh, but c squared is not c squared.
This is capital C.
Oh, got it.
Coulombs.
Gotcha.
Coulombs. Yes. Yeah, I wouldn't put c squared in the dimensions. I would always break it up into the Planck length divided by the Planck time.
Got it. Okay.
All right. Cool. So this is our first guess. Okay, meaning this gives us a place to look. We have a reason to be looking there. Why? Because we have bounds there. We don't know what the bounds are, but we want to know. Right? We want to figure out what are these boundaries, these 5 Planck constants. So here's one window into the 5 boundaries, right? It's this specific window, this arrangement between them, but now we want to know, does it just equal that? Well, here's the main form. We're going to have some set of actions, a geometric action, like say 2 pi, it makes a circle, okay? So you're going to look for, back up. We want to algebraically, geometrically code what's going on. So we're looking for any algebraic, geometric, simple equation that we could make sense of. That's the big deal, that we could make sense of. If it has 12 pluses and divides and all kinds of components, no, it needs to be as simple as possible. So we're preferentially giving credit to things that are simpler than things more complex, okay? Now you want to leave some room for, have some complexity, because when you're making guesses, they're guesses. So be flexible and keep track. Well, that one said it was close to, and so on. Keep a list of your guesses, because when you're pattern forming, you need a pile of things to be able to recognize a pattern. Anyway, we have a primary action, and then we have a primary boundaries. And that's literally this. So our boundaries are going to be what we just did every time. Just take the dimensions, put them in the limits of the dimensions. And then we're going to set this equal to our number. So constant, which in this case is this number right here. Okay. Now, our structure, this is a big clue. This is the reason we're going to be able to find pattern in this. So I did this forever. Actually, maybe I won't say what I was just going to say. I'll warm up to it more. When we search for this one, look how many digits we have. 1, 2, 3, 7, 8, 9, 10, 11, 12 significant digits, plus or minus 84 in the last 3, 4. Okay? So you might think of that as more like 10 significant digits, 10 point something, but I'm just going to call it 12, and I'll always just leave the plus or minus errors.
Yeah.
We want to keep track of how big the error is. It's literally our confidence with this measurement. Okay? Mm-hmm. Well, the thing is, if you did this pattern, what I just told you, and try, well, first of all, you'd have to say, well, what's the Planck length? What's its value? You can't do what I just said unless you have a number for it, right? The Planck mass, and the Planck time, the Planck charge. You need to know their exact values. Mm-hmm. So we have those, but should I explain how we got those, or keep going with this at this point?
Can you explain it in just a couple, like a sentence or two, just the general idea?
Yeah. So we took the Planck constants from all the constants in nature. Yeah. We have error bars on them because every constant you can put together to cancel as much as possible and say just end up with a single time dimension gives you the Planck time. But if you do several different ways, you get the Planck time with different error in the end. So the total error, yeah. So taking the total value of this with its error, yep. Okay, and then using this pattern, which makes just the Planck time there, yep. I started looking for ways to break up or just try to find an algebraic geometric relationship that got us to what we know this number is supposed to be. Yeah. And when I found one, actually quite beautiful one, right, then all the other ones had pieces that match. So I got a coherent system that's breaking, or that's algebraically coding that system. Then what do we get to do? If you find something's equal to 4 pi squared, times j cubed or whatever, you get some algebraic equation. Well, if you're using pi, you know pi out to any digit you want, right? Once you have an algebraic expression, you can now extend. So I took the measured values to ask Wolfram alpha what algebraic equations get us there, right? And then it said, oh, these, and the simplest, beautifulest one of them all is the one I picked. And then I said, okay, well, I'm going to assume this one's right, and now I know the rest of the digits for the Planck time. That's basically what we're doing. So, and
Planck time was the one you started with.
Well, I can't report it like that because I do hours and hours and hours for months and months and months. So I have no idea which one I asked first, but I asked them all.
Yeah.
So, and then I asked them all again, and I asked until I got a found patterns. Yeah. Okay. So yes, at this point, if you were to try to play this game, given what is on Wikipedia for these values, you would have to stop the game at 5 significant digits. Okay, you would get too much error happening at 6, 7 from then on. But with these exact values, you can put as much accuracy as you want. Okay, now we don't only need out to 14 significant digits because there are no measurements that measure that accurately. Okay, anyway, but we now have the 14 significant digits from all these 5. So we can give these values, and now we can check, do the values, are they right? Right? There's lots of ways for us to now check. Did we get any of them wrong? There's some really beautiful ones that will all come together. But now in this pattern, if you were to check this constant, you wouldn't find anything interesting. You wouldn't find it. If you deleted this and said, okay, well, let's be a little less accurate. Just give me the closest thing that is interesting. Yeah. Let's back off 1. Okay, now check. I don't know. Well, maybe we'll just do this one for an example, right? Yeah. But then, okay, if you don't find anything interesting, to back off. I realized that at some point, I'm like, I don't know how complex the system is I'm trying to make sense of. It could easily have another component in it, one more component in it, right? And if that's the case, then that would explain why the Planck constants are all only known out to approaching the 7 significant digits. There must be something else there changing the game, okay? So, and if you translate that change, then it would all be coherent again.
That's part of why maybe you had the interest in the root or logarithmic functions, limiting digits and things.
Yes, kind of. Yes, because the digit game here becomes important. Well, I started saying in my head, if I can't get an exact answer because there's something else in play, then just always back off every digit. I checked the pattern for this constant by putting in this whole number and then deleting this one and checking, deleting this one and checking, deleting this all the way down. Now, I usually stop around 3 because I don't trust anything under that at all. It just wouldn't be valuable for me. At 4, it starts to become something valuable. Why? Because if I got a computer to draw a really good circle for you, right, this big even, and you came and tried the best you could to measure its circumference and diameter with the best you can do with your eyes, well, all of us wouldn't even have the best eyes. You get a human with the best eyes to try to do that, right? They're not going to get the 4, 5, 6 significant digits. They're going to get 2 or 3.
Yeah.
Okay, so yeah, and that means that this number is seen far more accurately than we can.
Yeah.
Right? About here is about where we could see it. If we were looking at that thing exactly, right? Yeah. And the rest is even more precise. All right, so I would back off, and then I would keep a list of every answer Wolfram alpha kicks out. Not every answer that could possibly count as an elegant solution, right? Anything that's made up of only a small number of interesting things like pi or a constant that means something that I can turn a story out of, right? Then, with that list of possible answers, I have to put that aside and go to the next constant and get all of its list of possible answers. So after doing that for every one, many times, noticing this hinge point around 7 significant digits, I also had noticed that there's a constant, a very specific one, the Planck length times the Planck mass over the Planck charge squared, that plays some sort of special role. Why? Because if you put and let's just say the measured numbers, not the one we already have up here accurately, put in the measured string of digits for the Planck length, the measured string of digits for the Planck mass, so completely different digits in each other, right? And the string of digits for the Planck charge, completely different digits again. But then those strings cancel. They cancel the digits. They, in combination, just go away, 0, 0, 0, 0, 0, all the way out to the 7th significant digit. It's a digit shifting scalar, right? It says whatever you are here, I'm going to shrink you by 10 to the negative 7, and then otherwise you're the same.
Yeah.
Okay, that's really interesting, right?
Like 1.
Yeah, okay. Now, this one's important. I'm going to end up giving it a symbol. It's our external boundary arrangement, okay? So I'm going to give it this symbol with boxes. It'll show up a lot. But where it shows up in our construction here is we just need to say 1 plus or minus the smaller one, which is going to be some terminal action on some terminal boundaries, okay? But I'm going to call this the terminal boundary because it's always that one.
Yeah.
It's not a variable boundary. This prescription here tells you which boundaries we put together. But all of those boundaries, no matter which one you put together in the system, they have a final closure set of boundaries, and it's always this. Okay, so I'm going to erase this and
The
put...
fact that it's odd and that it's 7 is interesting.
Uh-huh. So this is our structure. This is literally our cheat sheet that we needed in order to try to start asking questions from these concepts in nature, for all of them, okay? Because this is the prescription that allows us to actually find solutions, and it's beautiful. So once you have this, you can ignore this part at first, and that means I'm going to automatically know I want 1, 2, 3, 4, 5, 6, 7. That's the 7th significant digit. So I wouldn't even, now that I've done this 1,000 times, and I know this pattern is what we're trying to confirm, I would type in this number all the way, but I would look fast, look fast, look fast, and then start looking carefully, and then start looking carefully, because I know this is where our pattern is going to show up. But I don't know exactly if it's going to be on that digit. Why? Because this could be a 2-digit number. It could be 4 pi. It could be, right? It could be negative 4. It could be 1 over 4 pi. So it could be here. It could be there based off of this. This is a scaling around it, right?
Right.
Good. So that's the pattern. That's the whole pattern for not just all the constants in nature, but for all the mass division boundaries, for all any kind of balanced system that's based off of our minimum construction.
Yeah. It's what's interesting about that part is that it's like your balance point angle, and then when you shift the angle, one side of your line length gets a little bit shorter, the other side gets a little bit longer, but you start from it's perfectly equal and it kind of zooms in right here, but then when you start to get that asymmetry, it's going to shift a little bit.
So this is inherently an asymmetric construction, but it looks a lot like, I don't know, maybe the recursive equation, right?
Yeah.
Yeah, except for this scaling. So it's the basic recursion equation, except for the second component is always shrunk. So the big one and the small one, the big one and the small one. Anyway, with this structure, this is a very simple equation. You piece the world into big and small, and big and small both have boundaries and actions that are acting against each other. It's a balanced set, right? That's it. And when you ask the questions under this construction, put any constant of nature in there, put their dimensions and translate it in terms of the Planck constants, then this will pop out. Well, so far it's done it for all of them, right? We get a answer. Is it the right answer? How do you know? How would you know?
Check against other measurements.
You don't know with one specific one, right? If it's a beautiful one, wow, maybe it looks beautiful, but you don't even get the depth of why. So what we're doing is not assuming we're right. We're not saying we get the answers right. What we're doing is logging that answer, and if we find any other ones, we'll write them down too. Okay, so we're getting a pattern of answers, but now we're changing the game, because instead of trying to imagine something by being a genius, right? Which is a lot of weird responsibility, right? You have to somehow get something right that you've never actually conceived before. That's not really the best way to go. We're not even trying that now. What we're trying to do now is to put ourselves, instead of the field of false negatives, it's the field of false positives. Okay? We've got a possible set of answers. We change the game from essay question, in which you're non-expert. Here you get an essay question exam. Shit, I don't even know where to start. I don't know anything about this topic. Okay, well, you would definitely prefer a multiple choice exam, right? If you really have no idea where to start, multiple choice is always going to be better than essay. And what we've done here is given ourselves not a way to exact truth for sure, we've given a method to start picking among possible answers. We were stuck completely. This is getting unstuck. Okay, so every answer we get, we can recheck, and if anyone else comes to using these methods, using this structure here, and using the rules that we want the answers to be as simple as possible. And we mean that in an elegant mathematician's way, or in a geometric way. If you can represent the solution with symbols in geometry in a shorter, compact form, I'm interested in it. Okay? If you can get one better than the ones I've got. But what we're going to do now is go through a couple of the examples, the ones I have, right? And then maybe we'll go through at the end a couple of the ones that I'm hoping there's even a better answer for. Because I've gone through them many, many times. I'm not committed to them being right as they are. I'm committed to them being coherent. And what's happened is well, I really need to point this out. When we're going to multiple choice, this is the kind of multiple choice we have, the test, right? We're now transitioning. We got that. What is this constant of nature? We're going to have a multiple choice answer. We're going to have, Wolfram alpha answer 1, whichever one you find in there, what's the best. But let's say that you have Wolfram alpha answer 2. There's 3 of them even. There's 3 answers that seem like, well, there's only made up of 4 things. That could be simple enough, right? So you've written them down. You don't understand any of them, but you have 3. Well, is there any other choices here in the multiple choice? That's all Wolfram alpha gave you, but does it mean is it for sure Wolfram alpha is not missing anything?
Could be combinations of them, or
sure, maybe it could be too complicated and it's missing because of that, right?
Yeah.
But that means it's going to be really hard to get. When we're looking for the simple things, we're hoping there's a simple story there. This Wolfram alpha is not necessarily answering everything. Why? Because Wolfram alpha doesn't know about every geometric number we care about.
Right.
That's the only reason. Okay, it knows about pi and e and the universal parabolic constant and I and all the main sets. What's the ones it doesn't know about?
That's a good question.
Does it have a briefing?
Questions including je1, je2,
Ah.
2, je3, je4. Okay, our 4 division partition constants of our external domain. So it has no idea about these numbers. It also doesn't know about rotation. If you're asking questions relevant to these, it also doesn't know about our rotations. Right? It knows about the golden ratio. It knows about all of those. These are the only ones it doesn't know because it's from our model. Now, what do I mean? When we found the accurate, all the digits of the Planck time versus the one we've measured, that algebraic equation spits out the value of this to any digit you want. Okay? And when we did this one, it spits out this one, and this one spits out this one. So these equations that we married ourselves to have these numbers associated in them. So Wolfram alpha doesn't know about these numbers because it didn't marry to these equations for any reason, right? It also has no idea about these numbers, the partition constants. They're all just the consequence of our 1 over x plus x cubed over 2 pi equation, our hyperbolic vortex relationship. That's then set equal to just 2 rotations, I to the I, negative pi over 2, inside the mass boundary. So just from this equation, we get 4 solutions, je1, 2, 3, and 4. The partition solutions of this algebraic connection, okay? And it doesn't know about those. So you have to ask your question all the way through. You have to back up. You have to do this digit, down to there, and see, did I get any good answers? Yep, I got Wolfram alpha 1, I got Wolfram alpha 2, I got Wolfram alpha 3. Great, you just started. Now, you got to go ask, you got to put in je1 and ask your question again. Okay, then you got to put in je1 squared and ask your question again. You got to put in je1 to the 4th. You got to ask every combination you think is relevant. You got to put 1 over je1. So it's going to take some time to ask all of these, if you think these are the only things relevant to be asking in addition to what Wolfram was asking. It still takes a while because you have to do the squares and the 1 overs and like that, right? So it's missing these. Now, if you're systematic enough and smart enough to stay on top of asking with all of these, then you'll build up a confidence table of the possible actual answers. You might end up with 12, right? You might only still have 1, and then you're pretty confident, well, that's all, I can only go with that one. It's the only one I have. Okay. This is the pattern. So it can take a long time, or it could be short. You could check just Wolfram alpha, and it has none of these in the answer, right? And it would find it the first time. Or if it has one of those in the answer, it's going to take until you put that in there to get it. Now, I did it like this for a long time. Actually, to be fair, historically, I did it with just je1 for a long time. And I ignored je2, 3, and 4. because J1 explains, or J1 squared is the fine structure constant, and it was the aim. And getting the fine structure constant was so exciting, I really hyper-focused on just it. It took a little while for me to tell myself, if J1's a solution to this partition arrangement, 2, 3, and 4 are also, they can't be extracted from the story. They must play a role. And then I became interested in them. So I started asking questions, all the same questions through all the constants of nature, now with J2, J3, and J4. Still didn't get everything popping out. In fact, I published a book at that point with the best ones I got, okay? And then right after I published the book, it occurred to me. This equation has its solutions that look somewhere right. Here's J1, and J2, J3, and J4, roughly, just to give a picture with it, okay? Those are the numbers Wolfram Alpha doesn't know about, so I had to use them as my search space, which really is the thing that takes a lot of time. But also, these numbers can be represented in a different way. I had been representing them as their x and y coordinates, right? But there's another way to also talk about them. If I go into a radial, so radius and angle now,
Yep.
so J1 doesn't change in the way I talk about it when I do that. J2 doesn't change. Why? Because neither one of them have any imaginary component, right?
It's basically just
But
radius.
these two become different. Yeah, just the radius, that's all they are. But this one is from the origin, not from J1, all the way out to there. This is a length, that radius, I'm going to call that Jr. It's also here, right? This is also, wow, it's really hard to do that sideways. Okay, Jr. Okay, so this Jr and this J theta, which is also, here's our negative J theta, right?
Yep.
Those numbers are also in this construction, which means you now have to go back and also add Jr and J theta as your search space. And those are the tickets. Those will get you most of them. Those really were the stepping point for me. All right, so now we've got the prescription for how to do this once. Well, we have the prescription for how to do it every time, but we've only gone through it once, right? Questions at this point?
No, I don't want to get you sidetracked. So
Okay, let's do one.
okay.
And let's pick a constant of nature. Does anybody have one that they're already interested in, or should?
Let's do Planck mass.
No, I mean constant of
Oh,
nature,
constant of
not a boundary. Here's the list of constants of nature.
All right, what do we got? That's interesting.
That's amazing. The G factor, right? Is that the
Let's do the magnetic flux constant.
Magnetic
Yeah,
flux constant.
definitely
Okay,
like that.
what's the symbol for that?
Phi naught,
Phi naught. Okay.
capital Phi naught.
Yeah. All right. So magnetic flux constant. What's the number?
2.0678338848 times 10 to the minus 15. And that's units are meters squared times kilograms over seconds times coulomb.
Okay. Great. So now, what's our first step? How are we going to try to parse what this means?
Okay, so identify our units of dimension.
Okay. So
So we're
we're going to do a primary action of
mass.
boundaries. And this is what we're going to do now. So our primary boundaries are going to be equal to Planck length squared, you said, right?
Yep.
Planck mass, and then?
Planck time.
And
then Planck charge.
Okay, that's absolutely clear what we're doing, right? Right?
Yep.
You got it too? We're just taking the dimensions of the constant and translating into the Planck constants, right?
Yeah, okay, yeah.
Okay, so now we've got this part of it. That's the first part of our equation, and the second part is 1 plus or minus some terminal boundary and our terminal boundaries and terminal action. Okay, so now you can go ahead and put this number into Wolfram alpha with its power, right? And say equals x times this. And we have to give you the values for that. So let's give you the Planck time. We need the Planck length. We need the Planck charge. And we need the Planck mass. What are the full numbers for those 5 or 4? 5.39, 1258, 368, 32313 times 10 to the negative 44 seconds. Okay? I'm listing these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And I list 15 just for the error on the 14 because I actually only care to 14.
Yeah.
But I'm listing the 15. All right. The Planck length, guess we need them all in here. Just
Entering this into Wolfram.
yeah. You're going to type in the number for this guy, right? Type that whole number in and said equal to x times by Planck length squared, Planck mass, Planck time, Planck charge. And solve for x. So good, you get to see how long it takes, right? And if you set it up really well, you have all your constants set there and you can copy paste. It is easier, faster.
Yeah. Okay, so I think I've got input interpretation. So we've got our 2.06 blah 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 times 10 to the 15 equals x times, and then we've got our 10 to the 35, 10 to the minus 8, 10 to the minus 44, 10 to the minus 18.
Is there a squared?
Oh, forgot to
square that one. Yeah.
I'm squaring the
The Planck length.
Oh, length. Okay, that's my first.
Yep. And the nice thing is that the answers will be like many powers off if you miss one of those.
Right.
Right?
And okay.
Okay. What do we get? X equals. Scroll down. Maybe it'll tell us what x equals. 36.7762. Any way you can get it more digits? 36 point what?
36.7762. Step-by-step solution. Show all steps.
You can make it more digits by forcing the smallest thing with digits to have extra fake digits, and then it'll know. Oh, okay, and it'll give you more, but those won't be right. But the ones you want will be.
Right. So it looks like it's showing it. Is x going to be the intersection point between those two lines?
Okay. Sure.
Yeah, it looks like
sure.
right?
Sure, yes. But now we're interested in interpreting what this number means.
Right.
But we need to know it. Well, this is good enough. 1, 2, 3, 4, 5, 6. I wanted 7, but this is close. Okay, we'll be able to get it. We need to know that number. What is it? So click on that number. This one. Click on that number. Just let you do it. Okay, put it up in the window now and search that number. So you see what we're doing?
Yeah.
Okay. We've got down to this number now for our x, and we're trying to interpret what that number is. What is the value of our primary action? It's right now in this number form, which doesn't mean much to us. Okay. And we're going to search. He's going to ask Wolfram for anything. If anything pops up, then we're cool. But if it doesn't, he's going to then re-ask it with J1, and then J2, maybe Jr, and J theta, right?
So it doesn't show me at least anything obvious right away.
Agreed. Okay, so let's talk about this a little bit. This is what you see. Okay, it looks like a bunch of stuff that if you take the algebraic expression and you were forced to make a story and try to explain it to a 12-year-old, if it's possible, write it down. If it's not, skip it. Okay, so right now I'd say nothing. I'd hit more. Is more already hit? Okay. Every time I have to hit more, so that's part of the slow procedure. And then all of a sudden I got something I'm interested in. Ooh. 35, because there's no plus after that, right? So I got a 35 over, what's this R what?
RTA.
RTA to the fourth.
To the fourth.
Cool. Now, we know 35 is our first arrangement, so that could be something we care about. How simple is our RTA? Well, what does it represent?
That's a good question.
You can go to the bottom, and it'll tell you, it doesn't tell you what the constants are?
No, it does right here. Gotta go to that.
Okay. There, now click on it. It's the fractional area covered by the rule X triangle.
Oh, what's our rule?
Click on it, and it'll give you a picture.
Probably Rouleau. Oh, interesting. Oh.
Okay.
That's interesting.
All right, so this might have something to do with the story we want to tell about what this constant is.
Look at that. Circles.
Right?
It's an equilateral triangle.
Yeah.
With the intersection of 4 circles.
Like one face of our tetrahedron.
Yeah.
Yeah. Okay. Now, we don't know for sure that this is right, but we know this is now an option. Right? So it's an option. Let's we write it down, we keep it. We start listing them. Let's are there any more on this list, by the way, that you would count as close enough to tell a story from?
Oh, let's bring this back up. Silverman constant. That'd be interesting.
Yeah, but just the algebraically, do any of the rest of them count to you in your mind as simple enough, or would you move on? 'Cause I think I'd skip the rest of those.
Well, let's see. Some of these go up. This one's 5 theta sub m plus 32.
By the way, this one, the way we wrote 1, 2, 3, 4, 5, 6. So it's got all of them that we put in there. So all 6 that we put, and I put a box down here like that to remind me.
Yeah, kind of
so
like
I know the precision. Know how many digits it got right.
Oh yeah, I just mean like a little square with the.
Because if I'm going to compare it to other ones, it might be useful. Okay.
This one's 5 theta sub m plus 32.
Yeah. Okay. So that would be our 5, our n, and then our magic angle plus derangements of the fourth kind, which are temperature. To me, the plus makes this less attractive than this one, but we can write it down. And how many digits was it accurate to?
36.776, which was. It was missing the 2.
And 6. So 5?
Yep, fell apart at the 2.
Okay, that's still good. All right. Of course, the smaller this number, or I should say, the further this number goes from 7, the better this better be.
Right.
Right?
The nicer.
Yeah. To justify going further away, it better be a simpler answer, not a more complex answer. Okay. All right. So we got a couple answers here. Let's try. It's a big number, so let's do divide by J1. Let's start with J1.
Okay.
And the value for J1, and the nice thing is I'm kind of leading you to check the right ones first, but but you know the method would be to check them all.
Right.
And honestly, even if you find this one, in order to consider yourself having searched the space, you still need to check them all, no matter which one I said was right.
Right.
You might come back and say, hey, you missed this one, and I guarantee I've missed one.
Right.
Guarantee. You probably missed more.
Yeah, well, the combinatorics of putting them all together.
Yeah, so J1 is equal to 0.08542415333304. Yeah, so now do x divided by J1 here, right? And solve for x now.
Okay, so let me bring up, I want to copy that.
Or you could do multiply or whatever, but divided is going to be fun.
The whole thing. Oh, we're putting it back into the initial one that we solved for.
Yeah. And what do we get now? X equals
Pi.
Oh, we might think that's better than this.
Yeah, it seems a little bit better.
Okay, so now we got an x equals pi.
Well, it seems natural because this was made.
So you're saying this number here equals pi divided by J1? That's what you're saying?
Yeah, well, x was 3.14159. Approximately 5.
Yeah, okay, great. So awesome. So you see, this is the procedure.
Yeah.
Now this one shouldn't necessarily be thrown entirely away. This could be also true, another thing to talk about the system, right? There could be, this is
another part of the system.
So filling out your own test of multiple choice questions, right, is like the scientific method now. You're keeping track of all the things that could count, and you don't know exactly why until you get a whole set of them and you say, oh, these are all the ones that are connected. Therefore, I understand why these are all the answer now. They're all talking to each other. But good. So we just did one. Now we've only done 1/2.
So we took this and divided it by J1?
So we went back to the first equation that we tried to solve for with the magnetic flux.
And divided x by
which
J1.
looked like this.
Okay.
And we're going to move on because we're going to move on to the second half now. But just to be extra clear for everyone viewing, moving on means you've gone through times it by J1, times it by J1 squared, and divided by J1 squared. You tried them all and you checked for the simplest answer. Now, here, you're probably going to guess that pi is not going to get any more simple than pi or beautiful than pi, right? But still, you want to check them all.
Right.
Okay, so I'm going to erase this and put our answer in. We said our first section is now pi over J1. Good, so that's our primary action. Here's our primary boundaries. Now we want to put in the next part, 1 plus or minus. So you're going to keep your equation that you have written there. We're going to solve for this one. And maybe just to go with the way you're going to type it in, just put an x there.
Okay, so
But this one needs to be the Planck squared. Oh, sorry, the Planck mass over the Planck charge squared. Here's a shortcut. Just type this. 1 times 10 to the negative 7.
Okay, so.
Just so you don't have to retype all those
Yep.
digits.
So I'm going to add a parentheses around that first guy. So
And just put plus here, and if x is negative, then we'll know that it should have been a minus.
Oh, because that's what it all collapses into.
Yep.
Anyway.
Yep.
So just to make a procedure a little quicker.
So this is exciting. You guys are doing this the first time. We just used this prescription for the first constant of nature, and you found this piece, which is actually a pretty competent one, right?
Yeah.
I mean, once you got that, you're like, oh, that's probably it. The boundaries were just from our Planck constant boundaries, and now we're solving for, well, what's the terminal action that maintains that balance? And you can try to guess, but I think it's much more scientific to look. Right? So everyone should be extra clear that's watching. This is the procedure I'm using to look closer, reinterpret the pattern. Look closer, get a better understanding of which things count as the anchors of the pattern, right? And over. So I'm always given the best version I got, but it helps me reframe.
Mm-hmm.
Okay, what do you find?
So I think I've got this structured right. Wait. I don't know if it's
I'm going to need this one too. JR. We might need more. It depends on which ones you guys want to do next, but 8, 2, 6, 2.
Regular powers are both fine, but
so 1 plus x times 10 to the minus 7, which is equivalent to 1 over 10.
No, 1 times by 10 to the negative 7. There's no x in this one. The x is outside of it.
Yeah, right. Oh wait, is this?
that's beautiful.
Okay, so I've got enough here for you now.
Okay. 4.773253. Sure, red. So you got an x here of 4.773253.
And if you do zeros instead of fives, I did another 3 zeros at the end. It tries to change it to 4.770566. So we've got our 77
here.
Yeah. So 4.77.
And it goes
where we
to.
get our separation.
Okay, so somewhere right here is where our accuracy is.
Right.
Cool. So that means we don't care about this digit, that digit, this digit, because
Yeah.
it's not true to us. Okay. Cool. So now search for this value. What could that value be equal to?
4.77.
Do any of those to your brain seem like they should definitely be written down, or they're just all iffies?
Are all we
A
writing?
lot of them seem like iffies. I don't know if there's any that stand out too.
Are all we writing is 4.774 right now?
We're only doing 3 significant digits, and we're trying to get 5 right at this point. He's getting 4.7732.
4.7732.
Yeah. 2 pi over 3 to the 1/4, maybe? I'm not really happy with it. It doesn't get enough. No, I don't really like this. So now we'd have to go to the sequence of, well, let's put in J1, 2, 3, 4. Let's put in JR.
Mm-hmm. Okay, so.
And a normal way to do this would say, okay, we have a value of 4. So instead of dividing by, you're trying to get closer to 1. So this could be made up of this and something. So we're going to have it be multiplied by. Does that make sense?
Okay, so now I'm going to change, instead of pi over J1.
No. You're going to take your x now, and you're going to say JR times x. So you're going to put a JR in here, or you're going to put a J1 or J2, or you're going to try all those and see if x is now an answer that's geometrically clear.
Okay, let's bring this over here.
So like scale it, what's that?
Okay, so we're going to do x times JR, and we've got JR at 4.
Okay, what does he get? Well, do you get anything?
1.06527.
0.06527, 1.06527. Okay, and does that turn into anything according to Wolfram that's algebraically interesting or geometrically interesting? If you don't see anything, maybe delete the 7.
Otherwise, we've got 2 minus 3 p sub c, which is the simple cubic site. interesting.
That one's not too bad. Square root of 2 times omega 1. Do you know what omega 1 is?
I do not.
It's if you say x times e to the x equals 1, there's only one thing that solves it, where x is equal to omega 1.
So we've got root 2 times omega 1.
Isn't it root of 2?
Yeah.
Yeah. Root of 2 omega 1.
Right. Omega.
That could be an answer. What else do we have here? That's the Pauli random walk in 3 dimensions constant. That could be interesting. Square root of 2n over 3 times p3.
The simple cubic site is the site percolation threshold for a simple cubic lattice.
What was on the denominator here? 2 times 5 times p3
over 3.
over 3.
You mean the 10p3 over 3?
Yeah.
So 2n.
N is a 5 for me.
Got it,
Yeah.
okay. Now we came up to 1.465.
Okay. These are both answers that would be simple enough and count with the data. But this one is times by jar, and this one is times by jar, right? Yeah. Okay. Anything else? Back off one digit and see what it says. That's still within our errors that we care about, right?
Oh, e factorial over 4.
I kind of like that, and I really like that.
Is that secant?
Secant squared 1/4. Why? Because secant is what? Is it secant squared?
It was secant squared over 1/4. Or secant squared 1/4.
It's that.
Yeah.
And we already have this structure in our structure. Where?
We've actually seen that. Yeah.
Where have we seen this before?
It's the quaternion. Let's see. It's in the quaternion.
On the time boundary, what is the equation for the time boundary? Pi r squared, our r is hyperbolic sine, right? You guys remember this?
Oh yeah, you said it's
This.
through the hyperbolic sine.
Our base, the lowest base of our whole system is the time base, right? And its structure is square hyperbolic sine with an argument of 1/4 or 1/2 squared. Here, and the sines, cosines, if you have a hyperbolic sine, you have a hyperbolic cosine, and you have sine, and you have cosine. And if you have sine and cosine, you have secant.
Yep.
Right? So this is the same argument. It's the same argument structure, same division, just a different aspect of the same division. Anyway, that's why I really like it, because it's very central. So I picked that one. Now, as you can see, you could try to argue this or this, right? I picked as my solution for this right here.
So this is indicating like a half turn. You're gonna 180.
It's a split and a split.
Yeah.
Yeah, it's two-dimensional split. Yeah, orthogonally. So we rewrite this and we say, okay, now we have, I'm going to put my symbol in for that now, okay? And say that the second half is secant squared and 1/2 squared. Yep, like that, jar.
Well, there's also an interesting
Times our n boundaries.
right side portion of it where the secant squared 1/2 squared, that is equal to 1 over cosine 1/2 squared, all that squared.
Yeah. So it's both of those things at the same time.
Right. Yeah.
And we already had that structure
Yeah.
from this.
Right.
Yes.
So this is telling us
So
create your cosine.
cohesion already in what we're doing. So that's why I picked this one. So, but to be clear, this does not mean I was right in picking this one.
Yeah.
Okay, that's not what we're doing. We're being scientific, and we're keeping track of the best answer, and we're picking among best. Now, until you make total sense, this one's not so bad to make sense of, because we're familiar with secants, I think, right? But if you picked an answer that you weren't totally familiar with, you'd have to keep going back until you did, until it made total sense.
Well, I think this is a good step to now say, okay, we've just gotten to an answer, but what was our initial question again?
Yes.
Magnetic flux constant.
Magnetic flux
Well,
constant.
what is
Let's go back.
flux constant?
Let's go back and
Right.
interpret it. Good. So now what are we saying magnetic flux constant is saying? What is it geometrically? What's the algebraic story?
Yeah.
Right? Well, it's a thing made up of a big piece and a little piece, right? Like everything in our external construction is. And the big piece is an arrangement between the dimensional boundaries of length squared, meters, or sorry, mass, like mass, and time and charge, right? So this arrangement between those boundaries connected under a flip and a division of J1.
Yeah.
What do we care about J1 again? What is it? What is J1 squared? The fine structure constant.
Oh, right.
Responsible for all of chemistry.
Yeah, I can't remember which one it was.
Yeah. Good. So J1, that's the same J1. This thing that's really, and it's also J1 times by the Planck charge equals the electron charge. So, I mean, literally responsible for all of chemistry.
Yeah.
Okay. So right there, good reason to believe it. We love this number and we love that number. Okay, but we need to interpret what they mean.
Yeah.
How do you interpret this?
So I think from the context of magnetic flux, this tells us how do magnetic fields interact with each other, and it tells us that at really close scales they're going to be they really want to interact with each other. But it's going to be all the way to infinite scales because it's still going to be connected to the external boundary.
Okay.
So you're going to have a drop off in its intensity.
Yeah. Okay.
And what it's telling us is that the magnetic flux comes because we're doing a splitting of boundaries at the really small scales. And as a result, you can have different scales of how split they are. And the different splitting of how big of a difference do I have is going to dictate how much of that flux constant am I amplifying.
And he said splitting, right? Splitting, and it's also square splitting.
Yeah.
How many times in our model do we get splitting that comes squared? Every time. So this is great. Yeah, great. So this is the story I'm telling too, and that's much more coherent than when we started out with this number.
Great.
Right?
Yeah.
Even if it's wrong. Because it's a story that you could then parse and start to find out why it's wrong. It's a starting point that you now make progress with instead of our wheels are spinning and we're never making any new starts. Right? Great. So that's the procedure. And when you do that procedure for every single one, more meticulously than we did, you need to go through all the numbers it doesn't know. So it takes some time to be confident, right? But then you put together stories like, you start to put together the story from all the pieces.